Modern artificial intelligence is remarkably fluent in human language, but ask it to perform deterministic logic, and that fluency becomes a liability. The model guesses, approximates, and predicts based on probability, rather than holding a rigid line of reasoning. In formal mathematics, probability is useless. A proof cannot be 99% accurate. If a system hallucinates a single assumption, the entire logical structure collapses. To prevent this, mathematicians have spent decades building formal verification engines. For over 40 years, systems like Mizar have rigorously verified mathematical truth, line by line. Mizar offers absolute, verifiable truth, but accessing that truth requires a student to master an incredibly dense, unforgiving syntax. One missing semicolon or improperly typed variable stops the compiler cold. Bringing formal verification into the modern classroom requires an intermediary. We need a system capable of interpreting the fluidity of a student's natural intuition and translating it into the rigid syntax the compiler demands, without compromising the ground truth of the math. This interface shows QuaNThoR. It is an orchestration layer built specifically to bridge the gap between probabilistic AI and formal verification. Notice the design principles listed here. QuaNThoR is not a math-solving AI. It does not generate proofs on its own. Instead, it operates strictly as an intelligent buffer between the student's natural language and the Mizar compiler. A student starts by submitting a mathematical query in plain English. The phrasing can be conceptually fuzzy or entirely unstructured. The system processes that intent, formats it into strict code, and passes it to the Mizar engine. The feedback returned to the student is based entirely on the compiler's deterministic response. By restricting the AI's job strictly to translation and routing, the system ensures that the final verification grade contains zero hallucinated data. This visual breakdown illustrates the four architectural pillars. First, the container cube ensures isolated, reproducible code. Second, the route node explores and classifies student intent. Third, the theorem quantifiers represent rigorous ground truth. Finally, the support pillar highlights the pedagogical objective. A raw compiler simply rejects incorrect code, but by combining these concepts, the architecture creates an environment that catches errors, interprets intent, and safely guides the student. When a student hits submit, that query enters the system through a REST API endpoint. Before any math is verified, the routing engine classifies the payload into four pathways. First, proofread applies grammatical corrections. Second, draft Mizar transforms natural language. Third, verify Mizar executes code directly. Finally, needs clarification catches ambiguous requests. This routing layer acts as a firewall. By catching ambiguous requests early, it prevents invalid data from reaching the computationally expensive verification stage. In this architecture, the AI's intelligence is defined entirely by its ability to accurately route requests, rather than its ability to generate mathematical answers. If a request does require grading, it proceeds down the Verify Mizar execution branch. This is where the container-first architecture takes over. Every submitted proof is executed inside its own isolated, temporary, and highly restricted sandbox. Inside that container, the system interacts with the Mizar 8.1.15 binary. The payload is checked strictly against established mathematical rules. Once the compiler finishes, the sandbox extracts the pinpoint error data, then immediately shuts down. Because the compiler is entirely sealed off, the broader orchestration layer remains completely stable. A single student's fatal syntax error cannot crash the routing engine for the rest of the class. Sometimes a query is too complex to draft immediately. A student might reference a specific historical proof requiring external context. To handle this, the pipeline utilizes the Hippo-RAG architecture via the retrieve endpoint. This pulls specific document data from an external archive and injects it directly into the drafting process. To ensure that retrieved data is accurate and unambiguous, the system runs a neutro-sophic audit chain over the context before drafting begins. But adding external data retrieval introduces significant risk in a classroom setting. This brings us to the system's most critical limitation, its educational governance model. The official classroom deployment of QuaNThoR explicitly prohibits the use of open-source, localized large language models like Llama. Instead, the architecture mandates the use of strictly governed endpoints, like codecs or anti-gravity, secured entirely through fingerprinted WebAuth. Ungoverned local models cannot guarantee safe refusal behaviors or strict algorithmic compliance. Authorized cloud endpoints ensure that pedagogical guardrails remain secure. By enforcing these governance boundaries, the system ensures that student safety and algorithmic compliance are hard-coded into the workflow, rather than treated as optional features. When we step back and look at the system in motion, the entire interaction lifecycle becomes clear. A fuzzy query enters the router, is structured by the drafter, supported by RAG if necessary, and then rigorously graded by the Dockerized verifier. Then comes the vital final step. QuaNThoR takes the harsh technical errors generated by the Mizar compiler and translates them back into accessible, human-readable pedagogical feedback. The AI acts entirely as a tutor, explaining where the rules were broken. It never has the authority to override the strict deterministic grade assigned by the compiler. This creates a closed educational loop. The student's intuition is guided by natural language, but the mathematical truth remains entirely uncompromised. QuaNThoR is not designed to replace the rigorous review of human mathematicians. It is built to serve as the intelligent interface to that rigor. This isolation of the conversational layer from the verification engine ensures that the student's learning is guided by the unyielding rules of the logic engine, not the persuasive guesses of the AI. This is the core mission of the SecuredMe suite. It provides a secure pathway from definitions to discovery, empowering students through safe, verifiable collaboration.